Chapter 7 is on systems of equations. This chapter is just basically an extension of Chapter 6, so most of the things that we'll be going over should look a little bit familiar to you. Make sure before we get started on this lesson that you have already printed out the PowerPoint so you can follow along with us. Once you've gotten that together, you're ready to begin. A systems of equations is when you have two or more equations that use the same variables. The solution to the system is the one point or many points that satisfies all of the equations. If you were graphing, that would be your point of intersection. So you'll need to write that on your slide. And we're going to go over some situations on the next few slides. Okay, so as mentioned before, the point of intersection is going to be the solution to your systems of equations. Any kind of a linear equation is going to draw a straight line, just like you see. And the point where these two lines intersect is the solution to the equation. So this solution would be 1, 2. There may be times when you have equations that are parallel lines. Well, parallel lines never intersect, so therefore there can be no solution. But we can't just assume that these lines are parallel. We actually need to do the math here. So if you look at your at the slide here, if you touch it with the magnifying glass, it'll zoom in so you can see this a little bit closer. Okay, but you will see that the point of where it crosses the y-axis is 2. So if we're needing a slope and a y-intercept for this first line, our y-intercept is going to be 2, and we would rise 2, run 1. They're positive lines, so our slope is positive 2. So the equation for the first line is y equals 2x plus 2. Well, then our second line, our point of intersection, is -1. And again, we rise 2, run 1. So our equation would be y equals 2x minus 1. And as you can see, both of the slopes are the same. Therefore, we proved that these two lines are parallel. Therefore, they have no intersection and no solution. Okay, so in this example, what we're going to do is graph the first line. Well, as you can see, the first line is in blue, and it's already in slope-intercept form, so it's easy to graph. However, our second equation is not in slope-intercept form, so we need to do that first. So if we're solving for y, we need to subtract 2 from both sides. Our 2's cancel, leaving us with 2y equals 4x minus 2. Divide both sides by 2, and you get that y equals 2x minus 1. Well, as you can see, these two lines are exactly the same when put in slope-intercept form. Therefore, the lines are on top of each other, and we're kind of illustrating that on your slide. The blue line and the red line are the same exact line. So there are infinitely many solutions that would work in both of these. So let's just use one of the points just to prove what's going on here. Okay? If we test the point right here, we would have 0, -1. Well, if we plug this in, you would say -1 equals 2 times 0 minus 1. Well, 2 times 0 is just 0, so that doesn't even really need to be written. So you have that -1 equals -1. Okay, so just by looking at this graph and the two lines on the coordinate plane, what is the solution to the system of equations shown below? Well, as you remember, the solution to a system of equations is where the two lines intersect. So they're intersecting at 2, -2. So that is the solution to that system of equations. On the examples on this slide, we've been given two equations. The first is in slope-intercept form. The second is also in slope-intercept form. So both of these lines should be pretty easy for us to graph. As you know, we always start by plotting your y-intercept first and then using your slope to get to the next point. So we'll start with the first equation. The y-intercept is +6. And we're going down 2 over 1 for all of these points. Okay, and again, try to make your line as straight as possible. So that's our first equation. Then let's do our second equation in another color. So we'll do that in green. Start by plotting your y-intercept at -4. And in this situation, we're rising 3 and going over 1. So 1, 2, 3 over 1. 1, 2, 3 over 1. And so on. So you can see that on this graph, our point of intersection is going to be 2, 2, because that's where the two lines cross. Okay, so unlike our last example, our first equation is already in standard form. It's not in slope-intercept form. So in order for us to graph this equation, we'll need to get it in slope-intercept form. In order to do that, you have to solve for y. So remember, we have to subtract 2x from both sides. Our 2x's cancel, leaving us with y equals 2, that's a -2x plus 1. So to graph the line, we start by plotting our y-intercept at 1, and we go down 2 over 1, and we are going to graph this line. Our second line should be start at -3, and you're going up 2 over 1. So our second graph is in blue. And you can see here that our point of intersection is at 1, -1. Well, if we're going to check our work, all we need to do is plug in our value for x and plug in the value for y into both of our equations, and we can see if they're balanced. So you're going to say 2 times 1 plus -1 equals 1, which gives us 2 minus 1 equals 1, and 1 equals 1, which is true. So that works in the first equation, but it has to work in both equations in order for this to be correct. So we are saying that y is -1, so let's plug in -1 equals 2 times 1 minus 3. That's saying that -1 equals 2 minus 3, and therefore -1 equals -1, which is true, and our solution checks out in both equations, so we know that we got our answer correct. The next example is just another system where we have to solve for y before we're allowed to graph. So in order for us to do this, we need to subtract 3x from both sides. You get that y equals -3x minus 4. To graph this line, you're going to start at -4. So put your dot at -4, and we're going down 3 over 1, or we can also go up 3 over 1. And that's probably going to be a little more helpful for us in this example. Okay, connect your line, connect your dots to make your line. And that purple line is going to be for our first equation. Our second equation, we'll do that in green. So again, we're going to start at -4, and we're going to go down 3 over 1 or up 3 over 1. Well, if you're noticing this, these two lines are overlapping. Okay? Well, what does that tell us about the lines? How many solutions would we have on these lines if they're touching everywhere? That means you would have infinite many solutions. Okay, so let's summarize. You have 3 steps when solving a system of equations using a graph. The first thing you need to do is graph both equations. In order to do that, you either need to put the equation in slope-intercept form, or you can use the x and y intercepts. However, be sure when you're doing this method that you're using a ruler and graph paper to ensure that your solution is accurate. Second step, you need to think, are these lines intersecting? The point of intersection is your solution, and you need to make sure you label your solution. And last, you're always going to want to check your solution, just like we did in Chapter 6. Plug your answer back in. If both sides of the equation have the same number, then you know that you've done it right. However, in the systems, your equations have to be equal for both in order for the solution to be correct for both equations.
Okay, so now we're going to learn how to solve a system of equations using substitution. As you can see, there are 5 steps for solving a system of equations by using substitution. The first thing that you're going to want to do is solve an equation for one variable. That is usually getting y by itself or getting x by itself, or whatever variables happen to be in the equation. The second thing you're going to do is substitute the variable that you just solved for into the other equation. That's going to give you an equation that has one variable, and in step 3 you're going to be able to solve that variable in order to find the first half of the solution to the ordered pair. Step 4, you use the solution that you got in step 3 to plug back into one of the equations in order to find the other variable that you need to complete the ordered pair. The final thing that you should always do is just double check your solution by plugging it back into both equations. Alright, so here's our first example. The first equation says x plus y equals 5. The second equation says y equals 3 plus x. This is very helpful because step 1 is getting a variable by itself. You will notice that that variable is already solved for y. So what we're going to do is substitute this y equals 3 plus x into the first equation for its y variable. So it'll end up looking like this. We will rewrite the first equation, x plus y. But instead of writing y, we're going to open up a set of parentheses, and this equals 5. What's going to go in for y is the 3 plus x. So again, we took the 3 plus x here, that was y, and we plugged it into the first equation for its y. So now we want to get x by itself. There's nothing in front of the parentheses to distribute, so that what we're going to do is combine like terms. X plus x gives us 2x plus 3 equals 5. Then from here you're going to subtract 3 from both sides, and you get 2x equals 2. You're going to divide both sides by 2, and x equals 1. So we said earlier that just completed step 3, solving for that variable. So that gives us the first half of our solution, the x value of the ordered pair, or where the two lines will intersect, is 1. Step 4 is to plug this x equals solution back into the other equation to figure out your y. Since we know that y equals 3 plus x, now we know that y is going to equal 3 plus 1, which means that y equals 4. So the point at which these two lines cross is the ordered pair 1, 4. The final thing that you always want to do is just double check your solution. So if I go to that first equation, x plus y equals 5, I get 1 plus 4 equals 5. That is true, so that's a check. And then I get 4 equals 3 plus 1. When I double check it in the other one, 3 plus 1 is 4, so that's also a check. This is a good solution. Okay, so our next example. Solve the system of equations using substitution. Your first equation, 3x minus y equals 4. Your second equation is x equals 4y minus 17. Again, you'll notice that step 1 is done here because the second equation is solved for x. So we're going to substitute 4y minus 17 in for x in the first equation. So when we do this, we're going to write 3 x, but instead of the x again, we're going to open up a set of parentheses, minus y equals 4. Again, what's going to go in the parentheses is what x equals, which is 4y minus 17. So the next thing you're going to do here is distribute the 3 in order to get y by itself. So we get 12y minus 3 times 17, which is 51, minus y equals 4. Combine your like terms. 12y minus y is 11y minus 51 equals 4. Now we're going to add 51 to both sides, which gives us 11y equals 55. Finally, you're going to divide both sides by 11. And this time we learned that y equals 55 divided by 11, which is 5. So again, the first coordinate that we found on this problem is y, so we're going to put 5 in the y spot of the ordered pair. So now I know that the y value of the solution is 5. So again, this completes step 3 right here. Y equals 5. So step 4, we're going to use this 5, plug it back into the other equation where it says x equals 4y minus 17. So x equals 4y minus 17. Y, again, we know that y is 5 because we just found that in step 3. So we learned that 4 times 5 is 20. 20 minus 17 is 3. Finally, the last step that we should always get in the habit of doing is double checking this solution. So we're going to take this 3 and we're going to plug it back into both x's. We're going to take the 5, plug it back into both y's. So we should see that 3 times 3 for x minus 5 equals 4. 3 times 3 is 9. 9 minus 5 is 4, so that's a good solution. Now we go to the other equation. X is 3, so does 3 equal 4 times 5, which is your y, minus 17. That is also true because 20 minus 17 is 3, and 3 equals 3. Okay, so our final example using substitution are the problems 3y plus x equals 7 and 4x minus 2y equals 0. The first thing you'll notice is step 1, get x or y by itself. This is not done. So we need to solve one of these two equations for x or y. The easiest variable to solve for is probably x in the first equation. So 3y plus x equals 7. To get x by itself, I'm going to subtract 3y from both sides. And that's going to give me x equals 7 minus 3y. So, again, that was the first x. So now I'm going to plug in 7 minus 3y in the place of x of the second equation right here. So we're going to go 4x minus 2y equals 0. And again, what goes in for x is this 7 minus 3y. Now we're going to distribute 28 minus 12y minus 2y equals 0. Combine like terms. 28 minus 14y equals 0. Subtract your 28 from both sides. Negative 14y equals negative 28. divide both sides by negative 14, and y equals 2. So now we know that the second part of the coordinate of the solution is 2. We still got to find our x. Okay, so now we're going to plug in y equals 2 into the equation of x equals 7 minus 3y. So we get 7 minus 3 times 2. 3 times 2 is 6. 7 minus 6 is 1. So x equals 1. Again, your final step is to plug in your solution into both equations. So the first equation, 3y plus x, so we would get 3 times 2 plus 1 equals 7. 3 times 2 is 6 plus 1 is 7. That is true. So then we go 4 times 1 minus 2 times 2 for y. 4 times 1 is 4. 2 times 2 is 4. 4 minus 4 equals 0. So you get a check for that. So that is a good solution.
So now we're going to talk about elimination method. Eliminate means to get rid of something. So what we're going to try to do for this section is to eliminate a variable from one of the equations first. Alright, so now we're going to solve a system of equations by using elimination with either addition or subtraction. The first thing we want to do is we're going to look at our standard form, ax plus by equals c. And then we need to determine, alright, well, what variable have the same coefficients, or if they are exactly the same, if I have x over x or y over y. Alright, then we need to decide if you're going to add or subtract them in order to get rid of and eliminate that variable. Once you have solved for one, you're going to substitute it back in for the other equation so you can get the other variable. So now we're going to solve a system of equations by elimination using either addition or subtraction. The first thing you always do is put them in standard form, ax plus by equals c. And then you need to determine, alright, are the x values the same or are the y values the same? And if not, then you need to somehow finagle, well, what do you have to do to the x or to the y? Alright, then you're going to solve for one of the variables. If the x's are the same, then you're going to get rid of the x's. If the y's are the same, then you're going to get rid of the y's. And we're going to do a few examples next that will show us when we add and when we subtract. Once you solve for one of them, one of the variables, then you're going to plug it in by substitution, which you already know how to do from the previous slides before, and then you're going to solve for the second variable. Alright, so our first equation is x plus y equals 5, and then we have 3x minus y equals 7. Alright, the first thing you need to do, right here, which we have the x and the 3x, you want to make sure that we need to get alike. So, is it easier to add or subtract these to eliminate? No. But right here where we have the y's, we've got one positive and one negative. Well, in order to eliminate the y's, you are going to want to add these. So you put a long line underneath, and you want to add. When you add them, remember there's like an imaginary one here in front of both of the y's. So when you add them, they become 0. And don't forget there's an imaginary one here as well. So we have 4x equals 12. So in order to get the x by itself, we're going to divide each side by 4.
12 divided by 4 is 3. Okay, so this is just like substitution. We've solved for 1, and now we're going to plug it in. Now, you want to choose the equation that is easier to solve for your other variable. Well, we need to solve for y. So what I would do is I would replace the x in the very first equation right here in order to get y by itself. So I would say 3 plus y equals 5. And how do you get y by itself? You subtract 3 from both sides of the equal sign. 5 minus 3 is 2. So what I also say is, well, what does this mean with 3 and 2? 3 and 2 mean these two lines intersect at the point 3, 2. So if you were to graph this on a coordinate plane, this would be their intersection point, which is in quadrant 1. Solve the system using elimination when we have two variables that are the same. So this time we've got 4x and 4x. Well, this is pretty good because we can eliminate, so I'm going to put my long line underneath here. I can eliminate this by subtraction. What is 4x minus 4x? Well, 0. So this goes away. Alright, remember there's an imaginary 1 in front of the y. So we've got 1y minus negative 2y. Now be very careful. 2 negatives always gives you a positive. So 1 plus 2 is 3y. Alright, 7 minus negative 2 once again. 2 negatives become positive. 7 plus 2 is 9. Alright, so 9 divided by 3, y equals 3. Alright, so we need to substitute 3 in for y. It really doesn't matter. You can pick the top one or the bottom one of your original equations. I'm going to pick the top one. So I'm going to have 4x, because I'm solving for x now, 4x plus 3 equals 7. Okay, so I need to get this 4x by itself. So the opposite of positive 3 is negative 3, so I'm going to minus 3 from both sides. I'm going to cancel out. 4x equals 4. 7 minus 3 is 4. Divide each side by 4, and x equals 1. And my point of intersection, so if I were to graph both of these lines, they would intersect at 1, 3, which happens to be in quadrant 1 again. Alright, so we've got another one here. We've got 2x plus y equals 7 and 4x plus y equals 5. Alright, so I'm going to put my line underneath here because it's really easy this time. The y's are exactly the same. So if they're the same, you subtract. So I'm going to put my subtraction sign. That was a little big, but you get the point. They cancel out. The y minus y is 0. So now I've got 2x minus 4x, which is negative 2x, that's a 2, equals 7 minus 5 is also 2, but now be careful. 2 divided by negative 2, a positive divided by a negative is a negative 1. Alright, so I'm just going to plug them to the top one again. So it's going to be 2 times negative 1, I'm substituting negative 1 in for x, plus y equals 7. Alright. Well, 2 times negative 1 is negative 2. Alright, we need to get y by itself. In order to do that, we're going to add 2. The opposite of a negative 2 is a positive 2. 2 plus 7 is 9. So the point of intersection now is negative 1, 9. Do you know what quadrant that's in? It's in quadrant 2. So the intersection of these two equations is negative 1, 9.
So far we have solved systems using graphing, substitution, and elimination. Now we are going to look at how to use elimination with multiplication. What happens when our coefficients are not the same? When we have two equations with coefficients that are not the same, we need to use multiplication to get a coefficient that is the same. You may multiply one or both of the equations to use elimination. Let's look at the steps of solving a system of equations. The first step is to make sure that the equations are in standard form. Standard form is ax plus by equals c, which means a number times x plus a number times y equals a constant. Step 2 would be to look at the equations and determine which variable to eliminate. So you're looking for the variable that has the same coefficients. Step 3, we need to multiply the equations and solve. This would be if you have an equation that does not have the same coefficient for their variables. Then you would have to multiply one equation or both equations to get the same coefficient. Then you are able to solve for one of the variables. Step 4 would be to plug into find the other variable. So when you get your value for one of the variables, you are going to plug that into one of the equations and solve for the other variable. You will have an ordered pair as your answer. Step 5 is to check your solution. You are going to substitute the numbers in your ordered pair back into both equations and make sure that they are true statements. Let's look at this system of equation. We are going to solve it using elimination. We have 2x plus 2y equals 6 and 3x minus y equals 5. When we look at both variables, there are no coefficients that are the same. We can multiply, though, to make an equation that has the same coefficient. I'm going to multiply 3x minus y equals 5 by 2. By multiplying by 2, we will get 6x minus 2y equals 10. And I'm going to rewrite 2x plus 2y equals 6. Now we can look at the system of equations and we have a coefficient that is the same. Our y values have a positive 2 and a negative 2. We can eliminate those. Because the signs are different, we are going to add our equations to eliminate the y value. 2x plus 6x gives us 8x. Positive 2y plus a negative 2y gives us a 0, so those values cancel out, which is what we wanted to do in elimination, to eliminate one of the variables. 6 plus 10 gives us 16. Now we can solve this one-step equation by dividing both sides by 8. 8x divided by 8 cancels out the 8's, leaving us just x. And 16 divided by 8 gives us 2. So we have part of our ordered pair, which is our solution. Our x value is 2. Now to get our y value, we can plug in our x value into either one of the top equations. I'm going to plug x in for the top one. So we have 2 times 2 plus 2y equals 6. This equation only has one variable, which is y, so we can solve and get a value for y. 2 times 2 gives us 4. We're going to bring down our 2y equals 6. Now we need to solve for 2y. First thing we're going to do is subtract 4. We have a positive 4, so the opposite is a negative 4, or subtracting 4. 4 minus 4 cancel out, which is what we wanted to do to get 2y by itself. 6 minus 4 gives us 2. Now we are going to divide by 2 on both sides to get y by itself. 2y divided by 2 cancel, leaving us just y. 2 divided by 2 gives us 1. So in this equation, y equals 1. Now we have our ordered pair, which is our solution of 2, 1. We need to check to make sure that this works in both equations. So we would plug in our values. In our first equation, it would be 2 times 2 plus 2 times 1 equals 6. 2 times 2 is 4. 2 times 1 is 2. And 2 plus 4 equals 6. So it checks out in the first equation. Then we can plug it into the second equation. 3 times 2 for our x minus 1 for our y equals 5. 3 times 2 is 6 minus 1 equals 5. So it checks out in the second equation, which means that our solution for this system of equations is 2, 1.
Now we are going to look at this system of equations to solve by elimination. We have x plus 4y equals 7 and 4x minus 3y equals 9. Neither the x or the y have a coefficient that is the same. However, we can multiply this top equation, x plus 4y equals 7, by 4. When we multiply by 4, we are distributing the 4 to everything inside the parentheses, which would give us 4x plus 16y equals 28. Now I'm going to rewrite the second equation, which is 4x minus 3y equals 9. Now we can use elimination to eliminate the x's. We have to see if we should add or subtract to eliminate the x values. If we add 4x plus 4x, we are going to get 8x. So to eliminate, we must subtract. So we would have 4x minus 4x, which would give us 0, and eliminate the x's. 16 minus negative 3, which would give us a positive 19y. And 28 minus 9, which would give us 19. Now we have a one-step equation, which is 19y equals 19. 19 and y are being multiplied, so we need to divide both sides by 19. 19y divided by 19, cancel out the 19s and just leave us with 1y equals 19 divided by 19 gives us 1. So in our ordered pair, we have our y value, which is the second number in the ordered pair, as 1. Now to find the x value, we're going to plug in y equals 1 into one of our original equations. I'm going to plug it into x plus 4y equals 7. We have x plus 4. We're going to plug in a 1
for our y equals 7. 4 times 1 is 4, so now we have x plus 4 equals 7. X is adding 4, so the opposite of adding 4 is to subtract 4, and we're going to do that from both sides to keep it equal. So we get x equals 3. So our ordered pair for this system is 3, 1. Now we can check to make sure that this works in both equations. So to check it, we would plug in 3 for x plus 4 times 1, and that should give us 7. 4 times 1 is 4, plus 3 equals 7, which checks out. Now we can check it in the bottom one. So we would have 4 times 3 minus 3 times 1, and that should all equal 9. 4 times 3 is 12. Negative 3 times 1 is negative 3. 12 minus 3 would give us 9, which checks out. Now we are going to look at this system of equations. 3x plus 4y equals negative 1, and 4x minus 3y equals 7. There is not a number that we could multiply 3 by to get 4, which would eliminate the x's. Nor is there a number that we can multiply this 3 by to get 4 to get rid of the y's. So we need to multiply both equations. You can decide if you'd like to eliminate the x or the y. I'm going to eliminate the y. So I'm going to multiply this top equation by 3 and the second equation by 4, which is going to give me a 12y and a negative 12y, which will eliminate. So I multiply 3 by everything in the first equation. 3 times 3x will give me 9x. 3 times 4y will give me 12y. And 3 times negative 1 will give me negative 3. Then I'm going to multiply the second equation by 4. So 4 times 4x gives me 16x. 4 times negative 3y gives me a negative 12y. And 4 times 7 will give you 28. Now, because you have a negative and a positive, that means you're going to add the equations to eliminate a variable. So you have 9x plus 16x, which is going to give you 25x. Positive 12y plus a negative 12y give you 0, so those cancel out, eliminating the y's. Now we have negative 3 plus 28, which will give us a positive 25. Now we have a one-step equation. 25x equals 25. So to solve this, we need to divide by 25 on both sides. $25x divided by 25 cancel out, leaving us just 1x. 25 divided by 25 gives us 1. So, in our ordered pair, the x value, which is the first number in the ordered pair, is 1. To find the second number, we need to plug 1 in for x in one of the original equations. I'm going to plug it in the top one. So we have 3 times 1 plus 4y equals negative 1. So 3 times 1 gives us 3 plus 4y equals negative 1. To solve for y, the first thing we're going to do is subtract 3. This will eliminate the 3's on one side. So 3 minus 3 cancel out, leaving us just 4y. And negative 1 minus 3 gives us negative 4. Now we have 4y equals negative 4, which we can solve by dividing by 4. 4y divided by 4 cancel, leaving us just y. And negative 4 divided by 4 gives us negative 1. So our y value is negative 1. The ordered pair that we have the solution for this systems is 1, negative 1. We need to check this in both equations to make sure it's true. So we would have 3 times 1 plus 4 times negative 1. And this should all equal negative 1. 3 times 1 is 3. 4 times negative 1 is negative 4. 3 minus 4 gives us negative 1, which checks out. Then we'll plug it in the second equation. We have 4 times 1 minus 3 times negative 1, and that should give us a positive 7. 4 times 1 is 4. Negative 3 times negative 1 is positive 3. 4 plus 3 is 7, which checks out. Here is the last system of equations we will solve by elimination. We have 2x minus 3y equals 1 and x plus 2y equals 3. If we look, we have a 1 in front of the x. We could multiply this second equation by 2, and that would allow us to eliminate the x's. So I'm going to multiply this whole equation by 2. And when you multiply the whole equation, you need to distribute the 2. So you would get 2 times 1x, which would give us 2x, 2 times 2y, which would give us positive 4y, and 2 times negative 3, which would give us a negative 6. I'm going to rewrite the first equation, which was 2x minus 3y equals 1. Now, because 2x and 2x have the same sign, we need to subtract to eliminate them. So 2x minus 2x gives us 0 and cancels out the x values. Negative 3 minus 4y would give us 7y, which is negative. And 1 minus a negative 6 would give us a positive 7. So now we have a one-step equation, negative 7y equals 7. We can divide by negative 7 to get our y by itself. Negative 7 divided by negative 7 cancel, leaving us just with the y. 7 divided by negative 7 gives us negative 1. So in our ordered pair, y is negative 1, which is the second number in our ordered pair. Now we need to find the first. I'm going to plug y equals negative 1 back into the second equation. So we have x, which is still unknown, plus 2 times negative 1 equals negative 3. 2 times negative 1 is negative 2, which gives us x minus 2 equals negative 3. To get x by itself, we need to do the opposite, which is to add 2 to both sides. A negative 2 plus 2 cancel, leaving us just with x. And negative 3 plus 2 gives us negative 1. So our x value in this ordered pair is also negative 1. Now we need to check our answer to make sure that the solution is true in both equations. So we have 2 times negative 1 minus 3 times negative 1 equals 1. 2 times negative 1 will give us negative 2. Negative 3 times negative 1 will give us a positive 3. Negative 2 plus 3 gives us a positive 1, which checks out. In the second equation, we would plug in negative 1 plus 2 times negative 1, and that should give us negative 3. Two times negative 1 will give us a negative 2. And negative 1 minus 2 gives us a negative 3, which checks out.
Solving linear system word problems. Now we will be applying solving systems to real life situations. You have $22 in your bank account and deposit $11.50 each week. At the same time, your cousin has $218 but is withdrawing $13 each week. We want to answer two questions. When will your accounts have the same balance? And how much money will each of you have after 12 weeks? In order to do that, we need to set up a system of equations. So for unknowns, we will have x being the number of weeks, since we are looking for how many weeks they will be the same, and how much you will have after 12 weeks. And our other variable will be y, and that will be your total in the account. We don't know the totals in the account, so we will make y equal to, we know that the first one has $22 plus they add $11.50 per week. So however many weeks it was, $11.50 added. The second one, same thing. We don't know their total, but we do know they have $218 in there, and that they withdraw $13 each week. So this should actually be a subtraction, since we are withdrawing each week. So $13 per week. Now we will enter these two y equals equations into our calculator. Follow the steps you learned before to solve the equation, or you could use substitution or any of the other methods as well. And you will get x equal to 8 and y equal to 114. So that is the information you received. Now let's answer our questions. When will your accounts have the same balance? To figure that out, our answer is right here. after 8 weeks, because remember that the system is where they intersect. So that is the point at which they are equal. So the answer to this question is 8 weeks, since X represents weeks. And to figure out how much money each of them will have after 12 weeks, you will have to substitute 12 in for X in each equation. And when you do that, you will get, for the first one, you will get $62. And the second one will have, after 12 weeks, will have $160. Remember, they are only equal at that one point where they intersect, which is 8 weeks. This is a break-even problem. Suppose you invest $10,410 in equipment to manufacture in a new game board. Each game costs $2.65 to manufacture and sells for $20. How many games must you make and sell before your business breaks even? So if you're starting up a business and you want to know how much money you're going to make before you start earning profit, or how much money you need, or how many items you need to sell before you start earning profit, this is a good problem to use. So we first must identify our variables. Once again, X is going to be your number of games, because we have no idea how many games we've sold. And Y will be your cost, your expenses, because we don't know how much we need to sell. Then we will form two equations. One, we know that we've spent $10,410 plus $265 for each game that we manufacture. So X being the number of games will equal our expenses. Also, 20 times the number of games, 20 is how much you're selling them for, will give you your expenses as well, how much you're actually making. So once you solve this system, you will get that X is equal to 600 and that Y is equal to 12,000. Now to answer the question, it says how many games must you make and sell before you break even? Well, you must make and sell 600, since 600 is what represents our number of games. Here's another example of a break-even problem. Several students decide to start a t-shirt company. After initial expenses of $280, they purchase these t-shirts for wholesale for $3.99. They sell each t-shirt for $10.99. How many must they sell to break even? So like the last one, we will have X. This time it will be the number of t-shirts. And Y, again, will be our expenses. Our two equations will be $280 because that's what they spent to start the company. They pay $3.99 per t-shirt, and that's equal to our expenses. And they sell them for $10.99 per t-shirt, and that's equal to our expenses. Once you solve this system, whether you use elimination, substitution, graphing, or the calculator, you will get that X is equal to 40 and Y is equal to 439.60. Your answer to break even is 40 t-shirts, since that's what X represents. Here is the last word problem. A garden supply store sells two types of lawnmowers. Total sales of mowers for the year were $8,379.70. The total number of mowers sold was 30. The small mower cost $249.99. The large mower cost $329.99. Find the number of each type of mower. Okay, so we have to figure out our variables first. So our variables will be small mower and large mower because we do not know how much of each of those were sold. So let's make X our small mower, and so then Y would be our large mower. From there, we have two totals. One is $8,379.70, and the other total is 30. Well, what gives you $8,379.70? How much the mowers cost. So $249.99 times the number of small mowers sold plus $329.99 times the number of large mowers sold will give you the total that was sold. This is the total of number of mowers. So just X plus Y, the number of small mowers plus the number of large mowers will equal 30. And once you've used one of your solving systems method, you will get that X equals 19 and Y equals 12. Where they intersect is where they will be equal. Find the number sold of each type of mower. So therefore we have 19 small and we have 12 large.
Now we're going to look at linear inequalities. Just as you have used inequalities to describe graphs on a number line, you can use inequalities to describe regions of a coordinate plane. For example, in x is less than or equal to -1. We graphed it like this on a number line. However, on a coordinate plane, x is less than or equal to 1, we graph a line at 1, like this line right here, and then we shade. We're shading in this entire region. All that's in purple would be shaded in, and this whole region here would be considered the solution to x is less than or equal to 1. Here's an example of a linear inequality. The solutions to an inequality would be the coordinates of the points that make the inequality true. For example, in this inequality pictured here is -2, 3, which is an ordered pair, a solution. If we look on this graph and we go to the left for -2, up 3, this point would fall right about here. It is within the shaded region, therefore the answer is yes. This ordered pair is a solution to this inequality. It's important to note that points on a dashed boundary line would not be solutions. So in this example, this has a dashed boundary line. So a point right here would not be a solution. Similarly, points on a solid boundary line would be solutions. Now we are ready to graph an inequality. The steps we take in graphing an inequality is first to make sure that the inequality is solved for y. In this case, our inequality is solved for y. We're going to locate our y-intercept, which is -1, and our slope, which is 3. First thing we're going to graph is our y-intercept. It is a point on the y-axis, remember, and it's at -1. There's my first point that I'm going to graph. Next point comes from doing the slope from the y-intercept. Since my slope is a +3, I'm going to rise 3, 1, 2, 3, and go to the right 1. Now that I have 2 points on this coordinate plane, I can draw my boundary line. I see that my inequality symbol is greater than, which means I'm going to have a dashed boundary line. It's not going to include any point lying on the line. So I draw my dashed boundary line through my 2 points. And I'm going to go through this graph because I have some shading to do. Since my inequality symbol was greater than, my boundary line is, everything shaded is going to be above or greater than this boundary line. The area to be shaded, therefore, would be all of this area above the boundary line. And when you shade in all the quadrants that are above this boundary line. Notice everything below the boundary line is not shaded. Okay, so we're going to practice graphing inequalities. Since our first inequality is already solved for y, we can begin graphing by locating the slope and the y-intercept. The slope in this inequality is going to be a -1. There's an understood 1 that's in front of this x right here. And our y-intercept is 2. So we would start on the y-axis at +2. And since our slope is a -1 or -1/1, we are going to go down 1 to the right 1. Since our inequality symbol is less than, we're going to draw a broken line or a dotted line for the boundary line. And since the inequality symbol is less than, we need to shade what is below the boundary line. And in this case, below this boundary line is going to be everything to the left. So, all the area that is shaded in red would be considered solutions to this inequality. Every ordered pair that could be located within the shaded region would be a solution to this inequality. The boundary line, since it's broken, would not be part of the solution. For the next example, we need to rewrite it because it broke off a little bit. And it was 4x minus 6y equals 18. Oh, not equals. It was greater than 18. Let's make this into a greater than. Greater than 18. So since this inequality statement is not solved for y is not by itself, we need to do some inverse operations to solve for y or get y all by itself. So the first inverse operation would be to minus 4x. Whatever we do on one side of the inequality symbol, we must do on the other side to keep it balanced. Positive 4x minus 4x cancels out. Leaves us with a negative 6y is greater than negative 4x plus 18. Those cannot be combined because they are not like terms. One more inverse operation in order to get y by itself would be to divide everything by negative 6. Since y was being multiplied by negative 6, if we divide, it would make these negative 6 cancel out. And our inequality now would change. Since we divided everything by a negative number, remember the inequality symbol changes or flips. Instead of greater than, we need to change it to less than. It's an important step to remember. If you multiply or divide by a negative number when solving inequalities, you must flip the sign when it's negative. Negative 4 divided by negative 6, negative 4x divided by negative 6 simplifies to a positive 2/3 x. And then positive 18 divided by negative 6 is negative 3. So now that we have this inequality solved for y, meaning y is by itself, we can locate our slope. And our slope is 2/3. I'll just put a box around it. Slope is 2/3. Our y-intercept is going to be negative 3. So we always graph with the y-intercept first. Going down on the y-axis, 3. Put a point at negative 3. And then our slope is 2/3, so we would go up or rise 2 and go to the right 3 to make our second point. Again, our boundary line is going to be broken because this boundary line is going to represent less than, and it's not equal to, but everything less than this boundary line. And since it's less than, we're going to shade what is below the boundary line. The solution to this inequality would be everything that is shaded in blue on this graph, and it would not include any ordered pairs or points that would lie on the boundary line, but everything that is below the boundary line. Now we're going to answer the question,
Are the following points solutions to the linear inequality shown? Our answers to these questions would be a yes or a no. To look at the first point, -1, 3, we could graph it. -1, 3 would fall right here. Since it's within the shaded region, the answer to the question, is this a solution, would be yes. Next, we look at the point 4, 2, or the ordered pair 4, 2. If we were to graph 4, 2, it would be here. Since it does not fall within the shaded region, then the answer to this question, whether this is a solution, would be no. We look at 0, 0. 0, 0 would be right here. Since 0, 0 is not part or within the shaded region, the answer to it being a solution of this inequality is no. The ordered pair -5, -4. -5, -4 would be right here on the graph. The answer is yes, it is a solution to this linear inequality because it falls within the shaded region. The ordered pair 2, 3 on this graph would be right here. The answer to it being a solution would be no, because it's not in the shaded region. The ordered pair 0, 2 falls on the boundary line. Since our boundary line is dashed, it does not include any points that fall on the boundary line. So the answer to this one is no, because we have a dashed line. The ordered pair 1, 2 would fall right here. It is not on the shaded region, therefore it is not a solution. Remember, this one fell on the boundary line right here, and it was not a solution because the dashed line. Had the line been solid, it would have included this point. Now we're going to graph systems of linear inequalities. We notice that both of our equations are solved for y. We can begin graphing the slope-intercept form. This one has a y-intercept of 0. So we start at the 0, make our point. Our slope is 1 over 4. From 0, I rise 1 and I run to the right 4. 1, 2, 3. I have my 2 points. I notice that my symbol is greater than, which means a dashed line. Draw our dashed line through our points as straight as you can. And we're going to graph we're going to shade what is above, since this is the greater than symbol. We're going to shade everything that is above this line, which would be this entire region above my boundary line. Now look at my next equation, and again, this one is also solved for y. I start with my y-intercept of +4, and I make a point. Do this one in blue. My slope, -x, is -1 over 1. So from the +4, I would have a rise of -1, I would go down 1, and a run of 1, so I move to the right 1. Remember, the slope is the same all the way through, so if I wanted some more points, I could just go down 1 to the right 1 again. Look at my inequality symbol, and since it's less than or equal to, I know that my line is a solid line, and this boundary includes all of the points on this line. Again, it goes straight through the points as straight as I can. To shade this equation, or inequality, we're shading what is less than this boundary. Everything below this blue line would be shaded. Up to the boundary line, and in this case, including the boundary line. Now, since it's a system, the solution to this system would be the area that is blue and red. Any ordered pair that falls within the blue and red shaded region would be the solution to this system of inequalities. For example, any of the points that I put in black would be solutions to this system. These are points, these are points. It would be all the areas where blue and red are. Not in just the blue and not in just the red, but in the blue and the red. Now we will graph this system of linear inequality. For our first equation, we see that y is already by itself. So this inequality is solved for y. However, the second one is not solved for y. In order to solve for y, I'm going to use an inverse operation here and add x to both sides. This would cancel my x's on this side. I can bring down my positive 3y, bring down my inequality symbol less than. I cannot combine my 12 plus x, so I rewrite them as x plus 12. One more inverse operation and we will have solved for y. Since y is being multiplied by 3, we'll divide each term by 3. Makes our 3's cancel, which leaves us with y. Our inequality symbol comes down as is, it does not change. My x divided by 3, this is really a 1x, becomes 1 divided by 3x. And my 12 divided by 3 becomes a positive 4. So here is my second inequality solved for y. Now that I have two inequalities solved for y, I can graph these. I'll graph the first one. My slope is going to be a -1. And we put that over 1. My y-intercept is going to be 4. And again, my inequality symbol is greater than, so I'll use a dashed line for the boundary line. I go to positive 4 on my y-intercept, plot a point. From this point, I'll do my slope, which is a -1. I will go down 1 and to the right 1. And I'm going to put a couple points here. And I'm going to draw my boundary line. My boundary line is dashed because my inequality symbol is greater than. Now, I will shade what's greater than this boundary line. And it's going to be everything above the boundary line. All of this area. Alright. Next, I'm going to draw my boundary line for my second inequality. I see that my slope here is 1 over 3. And my y-intercept is 4. So I'm going to go back up to 4 and make another point. And my slope is 1 over 3. So if I rise 1 and run 3, 1, 2, 3, here's my other point. Again, I'm going to use a dashed line because my inequality symbol is less than, and it does not include this boundary. If I'm going to shade everything that's less than this line, then I need to shade everything that's below the line. And I'm going to shade everything in the black that is below this line. It's going to include this part of the red. And all of this too. Everything below the boundary line is shaded. So I think you get the idea. Now, I'm going to try to show you what the solution to this system would be. Since it's an inequality, you know that there's more than one solution. This shaded region that has black and red would be considered all the solutions. So all of this blue, all of these points would be considered solutions of this inequality. All of these, and I'm not going to be able to give you all of the solutions, but anything in the area that has black and red shaded, not including this boundary line, but including this boundary line, would be included. So everything that's shaded black and red, and I'm putting some blue points in here, would be solutions to this system.